Welcome back to AI Paper Podcasts. Today we're digging into Clim, clustering-based iterative data mixture bootstrapping, a really interesting paper from NVIDIA and Georgia Tech. Just for the quick summary up front, Clim is a new automated way to figure out the best mix of pre-training data for large language models. The problem is these huge data sets, they don't have clear labels, and finding the best combination manually is just super hard and inefficient. So Clim's approach, it embeds datasets, groups them by meaning using clustering, and then it iteratively refines the data mix. It uses smaller proxy models and a predictor to figure out what works best. And the key result, they created this dataset called Climix. A 1B parameter model trained on it actually beat Llama 3.2-1B by 2.0% on average. Pretty cool. Plus, Clim helps automate the whole process, finds better data combos, and can even improve performance in specific areas like they saw a 5% gain in social sciences. They're also releasing two datasets, ClimbLab, which is 1.2 trillion tokens across 20 clusters, and ClimMix itself, the 400 billion token optimized mix. Great resources for the community.
So yeah, today we're unpacking how ClimB is trying to automate this tricky art of curating pre-training data.
That's a great summary. And it really is critical. As these models get bigger, the data we feed them, well, its quality and composition become absolutely paramount. We're dealing with data sets like Common Call, trillions of tokens. It's an amazing resource, sure, but it's also, a huge messy pile of unlabeled information. Figuring out the best way to use it, how to balance general knowledge with maybe more specific domain expertise, that's a massive challenge.
Yeah, you really hit the nail on the head there. It's not just about quantity anymore, is it? Just throwing more data doesn't always work. And like the paper says, the old ways, manually picking data or using simple rules, they just don't scale well. The interactions between different data sources and how they affect the final model, it's just too complex for our intuition alone.
Exactly right. And that's where ClimE comes in, offering a different approach. It's automated. It learns the optimal mixture. It lets the data itself, guided by these clever algorithms, kind of tell us the best recipe. It's moving it towards a much more dynamic, data-driven way of doing pre-training.
Okay, let's get into the nuts and bolts then. The ClimB framework, they break it down into three main steps. First up is data preprocessing, embedding, and clustering. Can you walk us through that?
Sure. So first phase, they take these big raw data sets, mentioned Nematron CC and Smong corpus, and they use an embedding model, Textillion 400 MV5 specifically. You can think of this embedding model like a translator. It maps every document into this high-dimensional space based on its meaning. The key idea is documents with similar meanings end up closer together in this semantic space. So we're looking beyond just keywords at the actual meaning. Got
it. So you create this kind of meaning map. Documents about similar things are near each other. What happens after everything's mapped out?
Then comes clustering. They use k-means, which is a pretty standard algorithm from the FAIS library. But what's interesting is they start with a huge number of clusters, like 1,000.
1,000 clusters. That sounds really fine-grained. Why start with so many?
Well, it gives them a very detailed initial look at the data structure. But yeah, 1,000 is a lot to manage. So the next step is crucial. They merge and prune these clusters. This happens in two ways. First, pruning. They kick out low-quality clusters.
How do they know which ones are low quality?
They use these fast text models. Think of them as little quality checkers. They're trained to look for things like, is the text educational, informational, or is it just, ads? They use annotations from Nematron 340B to help train these checkers.
Okay, so automated quality control filters out the junk. Makes sense. And the merging part?
For merging, they look at the centroids, the sort of central point of the remaining good clusters in that semantic space. If the centers of two clusters are really close, it means they contain semantically similar stuff, so they merge them together. This brings the number down to what they call enhanced clusters. They give an example, like going from 16 initial high-quality clusters from one source up to 21 once they added other data. It consolidates themes, basically, makes the next step more efficient.
Okay, so step one gets us organized. Raw data transformed into these quality-controlled, semantically grouped clusters. Now, step two, iterative bootstrapping. This sounds like the core engine of Clim, where they find the best mix. How does that work?
Yeah, this is really where the magic happens. Finding that perfect recipe, the right proportions of each data cluster, they frame it as a bi-level optimization problem.
Bi-level optimization, okay, break that down for us.
Think of it like this. The outer level is trying to find the best mixture weights the amounts of each cluster. The inner level is predicting how well the final language model would perform with those weights. Ideally, you'd train a full model for every single possible mix to see how it does, but...
Yeah, that's completely impossible, right? The compute cost would be insane.
Exactly. So Clim uses a shortcut, A predictor model, they used LightGBM, a regression model to estimate how good a given mixture will be. This predictor learns the pattern between different mixture weights and the performance they saw when training much smaller, cheaper proxy models. Ah, the proxy models. Right, so you train smaller, faster models on different data combinations.
Precisely.
And use how they do to train this predictor model.
You got it. The whole process is iterative. It starts with some initial guesses for the mixture weights. They mention using a Dirichlet distribution, which is sort of the smart way to guess based on how much data is in each cluster initially. Then they train these lightweight proxy models like 62 million or 350 million parameter ones on some of these mixes.
Okay, so you get some performance number from the little models, feed those results, mix weights and the performance, to the predictor. Then what in the next round?
The predictor learns from that data. Then, in the next iteration, the predictor helps choose the next set of mixtures to try. It doesn't sample randomly anymore. It focuses the search on areas of the mixture space that look promising based on what it's learned. The combinations it predicts will lead to high performance. And importantly, they also prune the less promising mixtures along the way, narrowing the search down. It's this iterative refinement that's key. That makes a lot of sense. You use the cheap proxy models to explore intelligently, letting the predictor guide you towards the good stuff without having to train the giant model over and over, bootstrapping your way to a good solution.
Exactly. The predictor gets smarter with each iteration as it sees more examples of what works and what doesn't.
And then, after a few rounds, they mentioned 3 iterations, the predictor spits out what it thinks is the final optimal mix. That's step 3.
That's it. After learning across these iterations, the predictor identifies the data mixture weights it predicts will give the best performance on your target tasks.
All right, that covers the Clim framework itself. Let's talk results. Did it actually work? How did it stack up against other ways of doing this?
Oh yeah, the results are quite strong. They compared Clim against several methods, just random data selection, and also 2 known techniques, Do-Re-Mi and RegMix. Table 1 in the paper shows Clim clearly winning out. This was for both 350M and 1B parameter models trained on 40 billion tokens. Across a set of general reasoning benchmarks, Clim's mixtures led to better average accuracy. Like, the 1B model got about 60.4% average accuracy, which was noticeably better than the others.
A solid improvement. And they mentioned these gains weren't just on the specific tasks used for tuning, right? They generalized.
Exactly. The performance boost was seen across all the benchmark tasks they tested, even the ones not directly used in the optimization loop. That suggests it's finding genuinely better, more general purpose mixtures, not just overfitting to the validation tasks.
And then they took their best shot. The 1B model trained on a bigger 400 billion token dataset using the Clim found mix, which they called Climix, and put it up against models like Llama 3.2 1B. How did that go?
That comparison in Table 2 is also pretty impressive. Their 1B model trained with Climix actually beat Llama 3.2 1B and AMD Alomo on average across a wider set of benchmarks, including things like MMLU, BoolQ, etc. They reported a 2.0% average improvement over Llama 3.2 1B, which, for models at this scale, that's a significant gain.
Wow.
And even their smaller 350M model trained with a Climix held its own against similar-sized models.
So it's not just finding better recipes in theory. These recipes actually scale up and lead to state-of-the-art results for the model size when you train on more data.
Absolutely. It really highlights how much leverage you can get from optimizing the data mixture, especially as you scale up.
Now, the analysis section in the paper was also really insightful. I was particularly interested in how they used Clim to optimize for specific domains within MLU, like STEM, humanities, social sciences. How did they manage that?
Right. This shows the flexibility of the approach. Instead of optimizing for general performance, they tweaked the objective. They told Clim, find the mixture that maximizes performance just on, say, the humanities validation tasks. And Figure 5 shows it worked. Clim consistently improved performance in these specific domains across its iterations. What's really interesting is that Clim, using its small proxy models for the search, often beat a baseline that directly searched using the full-size target model.
Wait, really? Using the smaller proxy models still led to better domain-specific results.
Yeah, it suggests the iterative search process with the predictor is really effective. And the gains were significant. That 5% boost in social sciences compared to random sampling stands out. It really drives home the point that the best data isn't universal. You can tailor the data diet for specific skills, which is powerful.
That is super cool. So you could potentially use this to build, say, a model really specialized for legal text or medical information by optimizing the data mix for that specific domain.
Exactly. It points towards creating more specialized models efficiently just by optimizing the data mix automatically.
They also did a bunch of ablation studies, tweaking things like the compute budget, how they allocated compute across iterations, proxy model size, number of clusters, the starting guess for weights. Any big surprises there? What seemed to matter most?
Well, mostly things behaved as you might expect, which is good. It shows the system is somewhat robust. More compute for the search, more iterations, more candidates evaluated generally helped, unsurprisingly. How you allocated that compute mattered too. They found a kind of balanced approach, like a 4.2.1 ratio of searches across 3 iterations worked well. So explore broadly first, then refine more deeply. Using larger proxy models, closer in size to the final target model, gave slightly better results. Makes sense they probably give a more accurate signal of quality.
Okay, what about the number of clusters? Was it super sensitive to getting that exactly right?
Actually, no. It seemed pretty robust. Within a reasonable range, changing the number of initial or final clusters didn't break things. Performance was fairly stable, although they did say going too fine-grained or too coarse probably isn't ideal. But there seems to be some wiggle room.
And the starting point. Did the initial guess for the weights matter much in the end?
Also, not a huge factor. Whether they started randomly or used that directlet initialization based on cluster sizes, the final performance was pretty similar. Again, it suggests the iterative refinement process is doing the heavy lifting.
That's reassuring. It implies the core idea, the iterative search and prediction, is solid.
Exactly. It seems capable of finding good solutions even if the starting conditions aren't perfectly optimized.
They also look at how the cluster weights actually changed during the search and which clusters ended up being important for general tasks versus those specialized MMLU domains. What did that analysis show?
Yeah, figure 8 is quite revealing. You can see the weights shifting around across iterations. For general reasoning, some clusters gain importance, others lose it. It's dynamic. Certain clusters ended up with most of the weight for general tasks. And when they looked inside those important clusters, they found a mix of topics. Then, when they optimized for specific domains, like humanities or STEM, different clusters rose to the top. It clearly shows different types of data fuel, different capabilities.
So it's not just about finding data that looks like the target task, but maybe finding the right combination of supporting information too.
That seems to be a key part of it. The interplay between different data types is complex, and Clim helps navigate that. High similarity to the task doesn't always mean highest weight in the final mix. They also showed that even using smaller proxy models like 62M versus 350M identified similar important clusters, suggesting the core signals are captured reasonably well even with smaller proxies.
Fascinating stuff. Okay, let's wrap up with Climix and ClimbLab, the datasets they released. What are they and why are they important?
So ClimbLab is the big one, 1.2 trillion tokens, already processed and organized into those 20 semantic clusters using their method. It's basically a ready-made playground for researchers wanting to experiment with data mixing. Climix is the result, the 400 billion token dataset built using the optimal mixture Clim found for general reasoning. And they showed in figure 1 that training a 1B model from scratch purely on Climix gives a significant edge compared to using other datasets with the same token budget.
So Climix is like their best recipe dataset for general models.
Pretty much. And interestingly, the optimal weights for Climix, shown in figure 6, were more balanced across clusters compared to when they optimized for continuous pre-training. Releasing both datasets is a huge contribution, really. Gives the community tangible resources to build on.
Absolutely. Having access to these clustered and optimized datasets is fantastic for pushing research forward.
Okay, so to boil it all down, what's the big takeaway here? I think the core innovation is the automation. Clim provides this automated, iterative way to find really good data mixtures for pre-training. It takes the guesswork and manual effort out. It uses proxy models and predictors to smartly search the huge space of possibilities. And the result is better performance beating Llama 3.2 Gone B is a strong proof point, plus the flexibility to tune for specific domains. It's not just finding a good mix, it's the system for finding good mixes automatically. That's the real game changer, potentially.
Yeah, it's about making data curation itself a data-driven, optimized process, letting the algorithms figure out the best fuel for these incredibly complex models.
Precisely. As models keep scaling, getting the data part right becomes ever more crucial. Clim offers a very compelling path forward.
Well, this was a great look into Clim. Definitely feels like a significant step in how we approach pre-training, maybe even leading towards more easily specialized models down the line, it leaves you wondering, right? How much further can automated data optimization take us? What new capabilities will unlock when we let algorithms curate the perfect learning diets for our models? Food for thought. We'll definitely link the paper and the datasets in the description for anyone who wants to dive deeper. Thanks for tuning into AI Paper Podcasts, and we'll see you in the next one.